Greetings, my name is Artem Horalnuk, and I am one of the authors of the article DBSCAN Parallelization by Spatial Dataset Division and Hyperparameter Adjustment. This article was written for by 2024 workshop by Vadim Romanyuk, Sergey Pavlov, Svetlana Yarenko, Artem Horalnik, and Elena Smetanyuk. The idea under this article is to parallelize DBSCAN functionality to make it more accurate and make it faster and, just to be honest, speed up the algorithm of DBSCAN. So in this article, we presented the result of our experiments, and before your eyes, this is a very short presentation of what was done so far. The main problem of DBSCAN was based on that cluster analysis and the dataset division is very effective when possible. Clusters are not spatially scattered. So our idea was the problem of clustering tends to be almost trivial. The distance groups of objects can be more efficiently separated by the support vector machine, literally inspirable data, and projected onto a higher dimensional space to become linearly separable, or other similar approaches included k-means with evaluation, the optimal number of cluster using the Siglet cluster evaluation. So the criteria, to the contrary, potential clusters closely packed together and totally indistinguishable without considering spatial densities. If, for instance, the cluster have at least partially hierarchy structure. A marginal example of such structure is a dataset consisting of non-overlapping enclosed hyperspheres or hyperellipsoids. Let's be this. Let's take this. Or objects of similar form being irregularly distorted or non-convex. Non-convex. Another major example frequently occurred in practice is a dataset consisting of cluster bands where serpentine-like clusters have resembling structure. So the naturally DBSCAN algorithm could have been easily speed up if it was generally parallelizable. So unfortunately, the algorithm is of two loops, and there is the nested loop, which cannot be made independent of the outside loop. The outside loop, working with each point in a given dataset, is based on the range query which can be implemented using the database indexing. So going forward, we made an some such decision and make the experiments with barely minimum required data to make the DBSCAN algorithm working. So we make some examples of dataset compressed by 10 serpentine-like clusters with each cluster 1000 point. Let me show this. Each cluster 1000 point. And example of dataset comprised by 6 enclosed circle clusters, each cluster as well 1000 point. And here is our mathematics, and here our comparative computation, the statistics for the planar serpentine dataset. So what we can say here, that the comparative performance statistics for the planar serpentine provided here on the slide, and you can see that the difference with parallelization makes a significant work. Going forward, we have the computation experiments with the next step, where we provide another amount of circle dataset points and get the worst case of the planar serpentine dataset with 11,000 points and 11 clusters, whereas the best result is P87.35455 is produced by the best interval parallelized DBSCAN. And being honest, sorry, I just want to make myself visible. So comparative performance statistics for the planar dataset was built the first time, and the worst case of the planar circle dataset of 8,000 points and 8 cluster, where the best result of P44 and 9 is produced by the best interval parallelized DBSCAN here as well. So it was 8 clusters with 8,000 points, and the result before you add parallelized, making it its job. Going forward, we have another amount of experiments with the original DBSCAN performance versus which is above, and the best interval parallelized DBSCAN performance below. In the worst case of the planar circle dataset on the figure, on the previous figure, which was on previous on the previous image, that the black squares mark points assigned on the non-exact existing clusters, and red squares mark outliers. So the mathematics and the logic presented here, and let's go to the next image, which was the parallelized DBSCAN performance is the planar circle dataset worst case, with the dataset division into 50 above and 55 below intervals. So it means like subsets. So going forward, the next iteration of our results was that the parallelized DBSCAN performance in the planar circle dataset worst case with the 4 dataset into 20 above 10 and intervals. And the mathematics and an example of 3-dimensional dataset comprised by 8 serpentine-like clusters, and each cluster still contains 1000 points. The X, Y, XZ, and YZ views are shown below, exemplifying that such datasets bear distinct features of circle dataset. And the 3-dimensional serpentine dataset is provided here, so the result as well here provided, which is showing the significant speed up and the real result, how the parallelization work here. And our conclusion was not so simple, because the compared to the performance of the original DBSCAN algorithm, the parallelized DBSCAN performs more accurately, being extremely fast. The later straightforward inferred with the tables which was provided, where the average speedup exceeds 80 times for planar dataset and exceeds 300 times for 3-dimensional dataset. But still, you can see our conclusions here, because our solution also has some limitation. And one of the limitations is the poor performance on datasets with circularity divided into intervals isn't common for circle datasets, whose natural division would be a circular sector, especially for 3-dimensional datasets. Moreover, it is hard to divide, so that each cluster would contain approximately the same number of points within every subset. So in addition, the DBSCAN parallelization efficiently is impossible to estimate without known ground truth labels. So the main reason of the minus is just estimation. So please feel free to read our article, feel free to reach out us as authors to get more information. Thank you for your attention.